Okay, so in this section we'll be going over pressure and fluid statics in general. These are some of the topics we'll be covering in this section. So as previously stated, right, pressure is a form of stress, right, and it's a stress related to the normal force, right. Uh, so essentially, if you talk about pressure, pressure is essentially fluid is equivalent to a normal stress which in turn is equivalent to or subject to normal force or related to normal force, right? So when it comes to pressure, it's nothing but normal force over the area on which that force is acting, right? So since pressure is a form of stress which is equivalent to corresponds to normal stress, uh, and the corresponding normal force, essentially pressure is just the normal force exerted by a fluid per unit area. Some of the common units that pressure is assigned is first is a Pascal, which is nothing but 1 Newton per meter square, and is the SI unit, and is a very common unit that is used. Something often you'll also encounter is 1 bar, which is equivalent to 100 kilopascals, and 1 atmosphere, which is equal to 1.0135 bars, right? Just something to kind of be aware of. You don't need to memorize per se, of the common units that you might encounter during the course and also in real life. So since pressure is nothing but force per unit area, right, if you want to visualize this, right, so example given here is of two people who have the same area of the feet that they on which their weight acts, right? So it says that area of the feet is 50 inch square, right? But one of them weighs 150 pounds while the other person weighs 300 pounds, right? So it should not come as a surprise in that case that the pressure exerted by this person, right, will be higher and will be equal to 300 pounds divided by area, which is 50 in square, right? So that's how they got the 6 psi. And similarly in this case, it will be 150 pounds, which is the weight divided by the area, right, which gives you 3 psi, right? So the heavier the force, if the area remains the same, the heavier the force or the bigger the force acting on that area, the higher the pressure would be, right? It should be intuitive there, right? Now on the flip side, we can also say what happens if you have the same force acting. So you have a force equal to, let's say, 10 Newton. One acts on an area of 1 meter square, while the other force, which is also equal to 10 newtons, but now it acts on a much larger, let's say, 10 meters square, right? So in this case, the first case, the pressure would be 10 newtons per meter square, but while in the second case, the pressure will be 10 over 10, right? So that is just 1 newton per meter square. So if the force remains constant, then the area, if it acts on a larger area, the pressure will be less versus if it acts on a smaller area, right? So hopefully that is a straight enough explanation or understanding that you can grab of how pressure is just equivalent to normal stress. But one thing you have to keep in mind, something that we mentioned in one of the previous sections, is that pressure is equal to normal stress only when the fluid is at rest. right? So essentially the fluid is not moving, right? So always keep that in mind. If it's a moving fluid, it might not necessarily, pressure might not directly be equal to normal stress. So something just to keep in mind, and remember that this pressure equaling to normal stress is only for fluid statics, right? If there is no dynamics involved for the fluid itself. Okay, so couple of terminologies that come into play now when we are talking about fluid pressure. One is called as the absolute pressure, and the other is called the gauge pressure. So when you're doing, or what you have been so far talking about, and what you're so far perceiving is actually as pressure is actually the actual pressure that we have been talking about at a given position. So essentially it is measured relative to an absolute vacuum, right? So it's the absolute pressure or the exact magnitude of pressure that is there. When it comes to gauge pressure, now it is not with reference to absolute vacuum, it is in relevance or relative to the atmospheric pressure, right? The reason people talk about gauge pressure is often you are measuring pressure for all practical purposes in the atmosphere or roughly of an altitude close to sea level. So atmospheric pressure does not change dramatically unless there's a significant elevation changes, right? So it's like saying, like, if the atmospheric pressure, if you're at the ground floor versus at the fifth floor of a building, it will not really change as much. It will relatively stay constant, right? So often when you're measuring pressure, or the instrument that you use to measure pressure, it will not measure with respect to vacuum, rather it will be measuring with relation to or with respect to the atmosphere, right? So what you're measuring there is called as the gauge pressure and not the absolute pressure, and hence the name gauge pressure, right? So the way the gauge pressure is related to absolute pressure is just by this relationship right here, right? So essentially it's saying the gauge pressure is related to atmosphere, so hence you subtract atmospheric pressure from the absolute pressure, and that will be equal to gauge pressure, right? The other way around of writing is the absolute pressure is nothing but gauge pressure plus the atmospheric pressure, right? So this kind of plot helps you understand this, right? So the absolute pressure is the complete pressure that accounts for the atmospheric pressure plus the gauge pressure, which is related to the atmosphere. So if you add this up, what you get is the absolute pressure in relation to vacuum. Okay, so it's just something to keep in mind when you're doing homework problems or example problems, is the fact that, are you given, or in real life situation, that's where it comes in more in use, is like, are you being given the gauge pressure or are you being given the absolute pressure? Something that you should be aware of. So next up is a fact about pressure, right? So pressure, the question is pressure a vector quantity or a scalar quantity, right? And this is something that probably you have a misconception about. So since we initially talked about pressure is related to normal stress, which is just force over area, right? So area is a scalar quantity, but force is a vector quantity. So most students end up thinking that pressure is also a vector quantity, right? But this is not the case. Right? Pressure is actually a scalar quantity, right? Because at any given point in a fluid, pressure is the same in all directions. So if you have one point in the fluid, any direction that you pick, the pressure value would be the same. So since it's independent of direction, essentially it acts as a scalar quantity, right? So it has a magnitude but no specific direction, right? And so it seems a bit counterintuitive and hence the next slide tries to prove this fact. So now instead of considering just a point, we start off with a section or a region of fluid, right? So if you have a giant region of fluid, and instead of taking a point, you are actually taking a wedge, or you're considering a system or a volume that is a wedge, right? The height of this wedge is delta z, the length is delta x, and the length of this inclined surface is L, with delta y being the depth of the wedge, right? So if this wedge had a depth to it, that is delta y, and it is given to be just 1. So right, just to make life simpler, it's treated as a unit width or unit depth, right? So essentially it becomes like a 2D problem, okay, instead of 3-dimensional problem, right? So the first step is essentially do a force balance, right? So hopefully you remember from mechanics and solid mechanics that if you're doing a force balance, you try to divide into component forms and do a force balance in x direction, y direction, and z direction, right? So since we are considering only a 2D object or plane, we are just doing a force balance in the x direction and z direction, right? Now, so essentially, hopefully you remember from Newton's law that F is equal to ma, but since the fluid is at rest, the net force is should be just equal to 0 in each direction that is there, right? So if we want to compute the net force in the x direction first, we go ahead and start with looking at each phase and looking at forces acting on it. So if you look at the first phase, you have P1, and that is acting in the x direction, so it will have a component in the x direction on net force. So if you remember, pressure is nothing but force divided by area, so you can write the flip form of it, that force is pressure times area, right? So you have P1, that is the pressure acting on this force, times the area, so which is the height of this section times the unit width that is there. So this forms the area. Okay, now if you look at the second phase, there is no horizontal component because it acts in the vertical direction, so no contribution will be there from the second phase. Now the third phase that you have, it is at an inclined angle, so it will have a tangential or horizontal component and a vertical component to it, right? So the force acting normal to this surface or to the inclined surface is P3, which is the pressure, times the length, which is the length of this inclined surface, times the unit depth, right? So that is the unit depth, which is delta y, right? And that is known to be just 1, right? But that is the force or the total force acting in this direction, normal to this inclined surface. But what is the component of this force in the horizontal direction? So what is the component of P3 in the x direction, right? So it's essentially P3 times this area times sine theta, right? Now this force is acting in the opposite direction, so opposite or negative x direction, right? Hence you have this negative sign here. And this net force should be equal to 0, that is coming from Newton's law, right? So essentially a force balance, or force has to be conserved because it's not moving at all, right? It's stationary fluid, right? So similarly, if we do for a force balance in the z direction, we see there is no component of P1 in the z direction, right? Everything is in the x direction. But the second phase has a component in the z direction, and it is again given by the pressure acting on that phase times the area of that phase. And now when it comes to this inclined surface, you have a vertical component which is given by P3 times area, now times cosine theta for the vertical component. Again, this is acting in the opposite direction, so there's a minus sign. Right, so these are the pressures But in addition to pressure, since this is a finite volume of fluid, it will have a weight associated with it as well, right? So weight is given nothing but mass times gravity, right? So gravity remains constant, mass is nothing but density times volume, right? So what is the volume of this wedge? It is the area or cross-sectional area of this triangle multiplied by delta y, right? And a cross-sectional area of a triangle is nothing but delta z delta x divided by 2, right? So that's how you get this volume, right? Now this weight is also acting in the downward direction, so you have a minus sign associated with it. Okay, so that becomes your force balance in your x and z direction. Now if you realize that this delta z that is here and delta x here can be written in terms of L, right, you see that delta z is nothing but L sine theta and delta x is nothing but L cos theta. So if you end up substituting here, essentially you end up getting P1 delta y L sine theta minus P3 delta y L sine theta is equal to 0, right? So delta y cancels, L cancels, and sine theta cancels away, right? So essentially the force balance in x states that P1 minus P3 is 0, or the other way to put it is P1 is equal to P3. Now if you do the force balance in z direction, you'll get a relationship between P2 minus P3, and then there's the half rho g delta z, right? So now we come to the realization that, okay, we were talking or making the statement about fluid being the same, or pressure in the fluid being the same at a point, right? Not at a volume with finite region or area, right? So now if you consider the limiting case of the volume shrinking to a point, that means this delta z and delta x, how you want to put it, going to 0. At the limit delta z goes to 0, this term or the weight corresponding to it, right, will also go to 0, right? As a result, all you end up getting is P2 is equal to P3. So hence it can be shown that P1 is equal to P2 is equal to P3. So pressure in all these three directions are going to be equal, and since this theta is arbitrary, technically I could have chosen any theta degrees and this P3 will still be equal to P1 and P2, right? Hence this acts as a proof to show that the pressure is independent of direction, or is going to be the same in any given direction, right? So pressure, as we talked initially, is nothing but force over area, right? So if we are considering a volume of fluid as given here, right? So what is the force because of this fluid, right? What is the force acting because of the fluid? It's just the weight, right? So your force is nothing but just the weight of that fluid because of this volume right here, right? So weight is nothing but density times gravity, right, times the volume, which is delta z, which is this height, times delta x, times whatever this length is. Let's say it is delta y to make it even more general, right? So that is the force acting on this face. Let's say this face that we consider, on this bottom face that we are considering, right? So now that is the force, but now force, we computed this, but we need to find the area, right? So the area corresponding to this face which we are considering, or we are trying to calculate the pressure on, right? So the area of that phase is nothing but delta x times delta y, right? So this delta y right here. So now finally, if you want to find pressure, it is nothing but rho g delta z delta x delta y divided by delta x delta y, right? So these two cancels off. All you're left with is rho g delta z. Okay, so essentially your pressure is a function of density, gravitational force, and the height, right? So when it comes to pressure, all that you're concerned with for a given fluid is the amount or height of this liquid column, right? So the height of the liquid column or the fluid column, that determines the amount of pressure acting because of a fluid or a liquid or a gas, right? Now you see the way they have written it for P2 minus P1 as -1, or minus sign is there to account for that the weight is acting in the vertical direction, right? So just be mindful when they're saying P2 minus P1 is equal to minus rho g delta z, right? So that is what this accounts for, right? So all that the pressure or the difference in pressure at point 2 and 1 or 2 points, or the change in pressure, is dependent on the height of the liquid column, right, which is given by this delta z. Okay, so sometimes you will see it, so just be mindful of it. Instead of writing P2 minus P1, it might be P1 minus P2 is equal to rho g delta z, right? So just be careful with the signs when they write it, right? Okay. So with that being clear, right, we'll kind of come to a more realistic case or example where if we want to find pressure at any given point submerged in a liquid, right? So let's say this is a lake and this random point is what you're interested with. Let me make it a different color. And this random point is at a height h from the free surface, right? So the pressure acting on this point will be the pressure because of the liquid column or water column h, right? So that is going to be rho gh, but right, there is also air above it, right? It's not vacuum, right? You have atmosphere above it. So the atmosphere also acts or pushes or provides a pressure, right? So that exerts a pressure. So the pressure at this phase or at the sea level is if it's atmospheric pressure, you have to add that pressure to find this final pressure at this point, right? So let's say if you use this relationship out here, your P2 minus P1 is equal to minus rho gh, right? And what you're concerned with is trying to find P1. So P1 is nothing but P2 plus rho gh, right? But this point 2, which is out here at the free surface, is the atmospheric pressure, and hence you get P atmosphere plus rho gh, right? The other way to look at it is the pressure at this point. If you're trying to find the pressure at this point, that is equal to the liquid column because of the water plus the column because of all the atmosphere above it, right? These two fluids combined provides the pressure here. Often, since this atmospheric pressure remains constant, as we just talked about, if we are just concerned with what is the additional pressure, we represent it as gauge pressure, which just comes out to be rho gh, right? So if you're talking about gauge pressure, all we are concerned is the height of the water column. So it's just rho gh in that case. Okay, so with this kind of clarification, we move on to the next point or an example to kind of kind of nail or drill in this concept clearly, right? So here we have different points at different heights, where points A, B, C, let me just mark this. So points A, B, C, D, E, F, G are at height h, and then the point capital H and I are at a different point which is bigger than this height h, right? So the question here is, first of all is what is the pressure at point A? And given that you have point P atmosphere here and this height is h, right? We just talked about this. PA is nothing but P atmosphere plus rho GH, right? So now that we have PA, the question is, what is the pressure at P, B in relation to PA? Is it same as PA, smaller than PA, or greater than PA? Right? We just said now that pressure at B is going, or the height out of B is the same as H for point A, hence pressure at B, right? If you use this relationship, you'll see that you get the exact same relationship, and pressure at P is exactly equal to A, right? So the pressure is only dependent on the height of the liquid column, right? It does not depend on horizontally where in that fluid the point lies, right? And the force acting on the surface because of the pressure at that point acts normal to it, right? So hence this, you have an inclined phase like this, you'll have a pressure acting here, right? And now if you look at the pressure at C, right, it is at the same height or depth, let's say. So you'll have the same pressure, same thing with point D, same thing with point E, point F, point G, right? Now if I look at pressure at point, if I create another point, let's say Z, right? If I look at the pressure at point Z, right, first of all, which direction will this force on this surface act? It will act normal to it, right? And the question is, will PZ be equal to PA, less than or greater than, right? You have this at a lesser depth, right? So your H is smaller, or the other way to look at it is the amount of liquid column or amount of weight because of the liquid column is smaller, hence PZ will be smaller than PA, right? So the amount of liquid column, if you want to make an imaginary liquid column, you see the amount of liquid column for the point Z is much smaller than if it was for point E or point A, right? You have a bigger liquid column, so naturally the weight of that liquid or water is going to be bigger and larger, right? So as a result, PZ will be less than PA. Now if that is the case, what is the deal with PI, right? So similarly, you can say the pressure at I is going to be greater than PA because it is at deeper location, right? So you have larger liquid column, or the larger weight of the liquid column acting on that point I. Now the final question would be, is PI going to be equal to pH? Right? So the answer is, this is not going to be equal to pH, right? Because here you no longer have water. It is a different liquid that is there, which is mercury. So essentially you have the weight of liquid of water acting on this column, but here you have mercury acting in this remaining portion, right? While in this case, all the way to I, you have the same liquid I. Now everybody knows that density of mercury is going to be bigger than density of water, hence pH is actually going to be bigger than PI. So be mindful that when it comes to pressure, it's not just H or the height, but the density also that is dependent on. So if your density changes, you have to account for it, or if you're using different liquids to compare, you have to account for that fact. So considering the topics or points or characteristics of pressure we just discussed, that can be summarized, and essentially it is called as the Pascal's law, right? So essentially, if you have any 2 points, so Pascal's law essentially states that if you have any 2 points at the same elevation in a continuous mass of static fluid, right? So we talked about how the fluid has to be stationary, you will have the same pressure, right? That's essentially the example we were going about in the previous slide. So if you have 2 points, let's say A and then you have B, as long as this height is the same, you will have the same pressure at P and B, right? It does not matter horizontally where it is located, as long as the height or the liquid column is the same, right? Now you can say the same thing about when they say about continuous mass, is the fact that it does not have to be directly a pool of, right? So it can be a pipe, and somehow you are able to compute this height h about this free surface, right? And this acts as your point A, and then in this case you have point B, which is also at the same height h, right? So as long as this fluid is continuous and it is the same fluid, right? It's the same fluid. It cannot be different fluids, because then the density changes. You're going to have the same pressure at these 2 points. So same fluid, and it has to be continuous, same fluid. The reason for it being continuous is, let's say if you have this closed tank in this shape, right? Okay, and I created a wall here, right? So, and this whole fluid, this is filled up with, let's say, water, and then you're looking at this point A and the height here, right? Now this side is also filled with water, and you're looking at the same point B and this height, or sorry, a point B and the height here is the same h, right? But I can, since it's no longer continuous, but I kind of created a wall to separate it, in theory I can pressurize this container to have a higher pressure B, because this is no longer exposed to the atmosphere, right? So there is no exposure to the atmosphere at the top because it's completely sealed, right? And that's the whole point of it, has to be continuous mass of the same fluid, right? And the same thing, because of the same fluid, for instance, if this was H2O or water, if this was mercury, then definitely it's not going to be the same, right? So that is kind of the gist of these 2 points here. Same static fluid and continuous mass of the same static fluid, right? Okay, the other way sometimes Pascal law is defined is essentially rephrasing this first definition, right? So if you consider pressure applied at a confined fluid, so if it's completely closed loop, if you increase the pressure at a given point, that same increase will happen by the same amount throughout it, right? So if this was A and point B, if you somehow increase the pressure at point A, right, since pressure at point B has to be same as A, right, so PB's pressure will also increase, right? So that's essentially what this is saying. So now Pascal's law forms the basis of hydraulics, right, or hydraulic lifts that you might have seen, right? So essentially hydraulic lift works on the principle of Pascal's law, right? And this diagram kind of helps you explain things, right? So here you have a same continuous fluid, and it is confined, so it's closed, right? So it's not exposed to the atmosphere. But one side, the cross section of this piston is A1, which is clearly smaller than this pipe or this cross-sectional area of this piston, A2, right? So A2 is bigger than A1, right? So we know if these points 1 and 2 are at the same height, which is the case here, so these two are at the same height and same location, the pressure at P1 and P2 are going to be same, right? So P1 is going to be equal to same pressure, right? That is definition coming straight of Pascal's law and what we have considered so far about pressure. We learned about pressure so far, right? But pressure being the same does not mean the force is the same, right? Because pressure is nothing but force over area. So if you say F1, so P1, in the case of P1, it is F1 divided by A1. In the case of P2, is F2 divided by A2, right? Now these two have to be equal. That's what comes from Pascal's law. Hence you can rewrite that F2 divided by F1 is equal to A2 divided by A1. Right, so the ratio of the forces acting on piston 2 and piston 1 is related to the ratio of the cross-sectional area of the pistons itself. Right, so if A2 was say 10 times A1, right, essentially to say F2 over F1 is 10 times A1 divided by A1. So it is multiplied by a factor of 10, right? So if I apply a force at the piston on the face 1, so F1 is 10 newtons, I get, or I can lift, using this equation I can find that I can lift or apply a force of F2 is equal to 100 newtons on this face 2, right? So just because the area has changed but the pressure remains the same, the force gets multiplied, or you can enhance the force, right? So this is the whole concept of how you can use a hydraulic jack to lift your car, right? I'm pretty sure if you try lifting a car with your bare hands, you will have some difficulty doing it, right? But even somebody like me can use a hydraulic jack and easily lift a car without any problem at all, right? And the whole principle is based on this Pascal's law here, right? So this ratio that of the cross-sectional area of the pipes or the pistons that leads to an increase in net force is called as the mechanical advantage or ideal mechanical advantage, right? Okay, so that's how what the hydraulic lift is based off of, and that's what's the principle on which it works, right? So with that being said, can you give me another example? I'm pretty sure you've seen this in real life and you've come across it, where you can, by which you can get some mechanical advantage, right? So you apply some amount of force and you get multiplication of force on the other end. What kind of mechanisms can you use, or mechanism that you're familiar with provides this mechanical advantage? So the answer to that is pulleys. So you might have seen in wells, in lifting mechanisms, if nothing else in heavy machinery cranes that are there, right? They have a bunch of pulleys that they use to amplify the amount of force they can lift or move by not applying the same. So they help increasing the efficiency or the mechanical advantage, right? So similar to hydraulics or hydraulic jacks or hydraulic lifts, pulleys kind of do the same thing, but it's slightly based on a slightly different principle here, right? It's not based on fluids principles there. So it's just something, an additional food for thought. So next up, we'll be briefly covering different pressure measuring devices. These devices work on the principles that we just covered in the previous slide. So the first of this instrument is called a barometer, which is used to measure atmospheric pressure. A simple barometer essentially can be thought of as a test tube which is filled up with a working fluid. Most commonly it's a dense working fluid all the way to the, let's say, to the brim. Okay, and then you have a container, or essentially it can be thought of a Tupperware or something, with the same working fluid, let's say mercury, in it. And all you have to do is tilt this test tube and immerse it into the into this container or bath with the rest of mercury in it, and eventually you'll see this mercury level fall to a certain value and stay constant. Now, since this was initially filled with mercury, you have a vacuum inside of this, right? And the height of this mercury column, if you can measure it, and let's say it comes out to be h, right? That h can be used to measure atmospheric pressure, the height of the mercury column. And the way it works is based on essentially the definition of pressure and force balance, right? And we can look at that. So if you look at a system or try to balance the forces of this liquid column or mercury column out here along the height h, right? And that's kind of what they have it in this section, right? So you have on the top, your pressure is going to be approximately 0 since you have vacuum, right? Now pressure at point B, what is it going to be, right? This pressure at point B is the same as, at the same level as this free surface on these 2 points, and you have a same continuous fluid and the fluid is static, right? Right. So the pressure at point B will be the same as the pressure at this free surface, which is at nothing but atmospheric pressure because it's exposed to the atmosphere, right? So essentially atmosphere, the whole atmosphere of the earth is pushing down on that free surface, right? But now when you come to the bottom surface of this system that we're considering, we realize that it's going to be atmospheric pressure, but what is the direction of the force? Right? We always say it's on the pressure acts normal to the surface we are considering of the system, right? So in this case, it acts vertically upwards, right? So we have two pressures on the surface, on the top and bottom surface of the system. On the left and right, you have glass, right? So there is no pressure, or that's the boundary of this test tube, so there is no pressure here, right? So there is no pressure acting here, and even if there is, right, it will be equal and opposite, right? So it cancels off. Now the last of the, in order to do a force balance, we already computed the surface forces, and the only surface force will be static, will be pressure in this case, right? Now when the next thing that we also is there, that is called the body force, which is essentially going to be as a result of the weight, right? The weight is given by density, gravity times volume, which is the height of this column times the cross-sectional area, right? So that's rho GHA. Okay, so now if you have to do a force balance, right? So if you're trying to do a force balance, what is the net? Since the fluid is stationary, what is, first let's start with what is the net force, right? The net force will be P atmosphere on the bottom acting upwards, right, times the cross-sectional area, right, because it's positive. There is no force on the top surface, and the final force will be weight, right? So weight acts in the negative direction, so you have minus W, right? So if we spread this out or rewrite it, so it's P atmosphere times area minus rho G H area, right? Okay, so that is the net force that is acting, right? But we know since this fluid is stationary and it's not moving, this net force has to be equal to 0, right? Because F is equal to ma, there is no acceleration, right? F is equal to ma. Since acceleration goes to 0, right, the net force has to be 0, right? So from this we can see that this A of area is common to both these terms, so it can cancel out, and what we end up getting is P atmosphere minus rho GH is equal to 0, right? And hence, if you rewrite it, we get P atmosphere is nothing but equal to rho GH. So what this says is, if you know or can measure the height of this liquid column, and if you know the density of the material, G is a constant, right? You can find the atmospheric pressure, right? So that's kind of the goal or the working concept behind it. Now, the reason you use mercury is from the fact that since the density is high, the corresponding height of the mercury column required to balance this weight will be smaller, right? So from a practical standpoint of view, you need a smaller length of a test tube. Now, instead of mercury, let's say if you use a lighter liquid, let's say oil, right? So your amount of atmospheric pressure is still the same, right? So since if rho goes down, then you need a bigger height to balance the same atmospheric pressure, right? So you might need a considerably larger manometer, which can at times becomes impractical, right? So that's kind of the reason you try to use as dense of a liquid as possible to use if you're using a barometer to measure pressure. Now, something that comes off of from the principles of or the concept that we already learned in the slides previously was the fact that there is no area dependency on pressure, right? When it comes to pressure, it does depends on the height of the liquid column, right? And that's kind of what we saw here as well, or in the previous slide, that the atmospheric pressure is just dependent on density rho GH, right? So no matter what the area or cross-sectional area of the tube is, if it's a thinner tube versus a fairly big or thick tube, right, the height of that liquid that will balance the atmospheric pressure is going to stay the same, right? Because in all these three cases you have the same working fluid, right? So the density is the constant or stays the same, hence the height has to stay the same in order to get the same to be able to measure atmospheric pressure, right? So it's independent of the cross-sectional area, just something to keep in mind. Now you have seen a barometer, but when it comes to manometer, it works from the same principle, but the only difference now is you're not measuring atmospheric pressure, you're measuring pressure of a fluid, which it might be either liquid or gas, in a container, or let's say in a duct or a pipe, right? So it works essentially from the same principles, right? So we just saw how this height balances the pressure, right? So we go and use the same Pascal's law, right, principle. So let's say if you have certain gas in this container and you want to measure the pressure of the gas, right, in this container, okay? So, and then you have a working fluid which is probably a liquid and which is denser in this tube to measure the pressure of it, and it is connected to this container. So if this liquid settles down into this configuration, by measuring this height of this liquid column, we can measure the pressure of this gas in there, right? So the way this goes about is you have this boundary or the edge of this liquid on this side of the tube, right? We know the pressure at P1 is equal to P2 from Pascal's law because it is at the same level. So we essentially extend the point 1 all the way to 2 so that it lies at the same level and is the same liquid, right? So pressure at 1 and 2 has to be the same, right? Now for this liquid column, we kind of do go about the same similar force balance as what we did before, right? Now, unlike the last slide when we used a barometer, on the top side it is open to the air. So here what will the pressure be, right? It is open to the air on top, so essentially pressure on this face would be atmospheric pressure, right? So if I draw this section, you have atmospheric pressure on the top pushing down, you have P1 pressure or P2, however you want to say it, P1 equal to P2 pushing up, and then you have this weight of this liquid column pushing down, right? So essentially if you do a force balance, you end up getting that P2 is equal to P atmosphere plus rho GH, right? That's kind of what this is stating, right? So you have the atmospheric pressure, as you can see from this force balance, right? Atmospheric pressure acts down, the weight also acts down, that's why these two gets added up, that's why you have a positive sign, and that equals to the pressure P2, right? So now if you know pressure P2, technically you know pressure P1, and hence you know, since 1 is the interface or the boundary between gas and liquid, right? So if I want to draw 1, right? So there is certain force acting by the gas which constitute the pressure, and then that needs to be balanced by the liquid as well, right? Because of Newton's third law. Hence you can compute the pressure at 1, or you can know the pressure of the gas at the container, right? So hopefully that is straightforward and clear, right? But let me ask you one question and something that you have to be mindful of, right? Technically you're measuring pressure at point 1. You're not measuring pressure at this inlet point here. Let's say if I call this as point 0, right? So will point 0, what can you say about point 0 with respect to 1? Can you say point 0 is equal to P1? In reality, or theoretically speaking, P0 is not equal to P1, right? Because you have certain height or distance here. Let's say this is H prime, right? So there should be a difference in pressure at P0 and P1, right? But since the container has gas, so this fluid has gas in this channel, right? P0 is approximately P1, right? And this is because, let me just erase this. So it's approximately P1, right? Because how is P0 and P1 related, right? P0 is equal to P1 plus it is going to be minus P1. P1 minus rho GH tilde, right? But this rho is density of a gas, right? So this is a very, very small value, right? Right, so the pressure or the value of rho gh that corresponds to this pressure difference is approximately going to be 0. Hence you can say P0 is approximately P1. Right? So hopefully that makes clear. Hence when you're calculating pressure at 1, that is roughly going to be the same as pressure 0, since this fluid out here is gas. Right? It will be slightly different if this fluid in this container was actually a denser liquid. In that case, you cannot approximate P0 to P1, right? So just keep that in mind. Okay. So with that, we're kind of coming to the end of this first part here. So we looked at the barometer and manometer, couple of measuring devices. Now when it comes to measuring multiple fluids, I just wanted to be kind of briefly go through that, right? Okay, so when it comes to measuring multiple fluids, just think of essentially go about dividing into separate layers rather than doing together, right? You can do it together, it can get confusing, so I suggest at least initially try to divide into sub problems and kind of go about that, right? End of the day, the pressure constitutes or originates from the weight of the liquid column, right? So for in this problem, if you are trying to find the pressure at point 1, you have the weight of fluid 3, weight of fluid 2, weight of fluid 1, and the weight of the atmosphere acting on this point 1, right? So you have to add up pressure or the weight of that whole, all of these fluids, right? So if we want to subdivide this problem, right, let's say if I always try and compute at the edges of two fluids, right? So if you want to find first pressure at point A, right? Okay, so without doing, even if you don't remember the exact signs, right, you can use intuition to say, will the pressure at point A be bigger or smaller than pressure at atmosphere or the free surface, that is at this point, right? So pressure, let's say this point is O, right? So pressure at A is deeper, right? So if you're going deeper into the ocean, right, you're going to experience higher pressure. So hopefully you are clear with that, right? You're experiencing a higher pressure as you're going deeper into ocean because of all the weight of the liquid pushing on top of you, right? So when it comes to point A, right, pressure at A corresponding to pressure at O will be bigger, so you add the weight or the pressure corresponding to the weight, so it's like rho 1 GH1, right? Now P0 is nothing but atmospheric pressure right? So you are able to get PA, right? Now if you want to find B with respect to point A, pressure at B, right, PB is equal to PA. Will it be plus or minus, right? Point B is lower than point A, so you will again do add it up, right? Rho 2 GH2, right? Finally, if you want to find P1 with respect to point B, it is P1 is equal to PB plus rho 3 GH3, right? Now if you go ahead and substitute PB and PA in this equation, all you end up getting is this, right? So you will end up finding that P1 is nothing but P atmosphere plus rho 1 GH1, rho 2 GH2 plus rho 3 GH3, right? So weight exerted by this fluid and this fluid, right? So all three fluids and the atmospheric pressure, and you just add it up. Okay, so that's as straightforward as it, right? So something to keep in mind and will help you in solving problems when you're dealing with pressure or fluid statics, and that has to do with just thinking of this when you're trying to find, if I give you a liquid path, right, and I say this is atmospheric pressure as this is exposed to the atmosphere, so on the free surface you have atmospheric pressure. Let's say I give you two arbitrary points, 1 and 2 in the liquid, right? So 2 is at the lowest point or deepest, 1 is somewhere in between, and atmospheric pressure or free surface is at the top, right? So if I give you, if in the given I have given you P2 and if I ask you to find P1, right, and you have to do it with respect to P2, right? So P2 is given, so you know P1 and P2 are related by this height. If let's say if that height is given to be h, right? So P1 and P2 is related by rho GH2, right? Now even if you don't remember exactly what these signs should it be positive or negative, just think about it in this way, right? Is the point at pressure at point 1 above or below 2? Right, in this case it is above 2, right? So will the point pressure at 1 be above or bigger or smaller than 2? Right, remember again, pressure is just the weight of the liquid column. Since it's above, there's less liquid column, there is less pressure or weight acting on at 1 because it's above it compared to 2, which is much deeper. So there's a larger liquid column, right? So pressure at 1 will be less than pressure at 2, right? Hence, respect to 2, it will has to be smaller. So you'll have to subtract this, right? So, but now on the flip side, if I gave you, so this was problem A, right? On the flip side, if I give you pressure at 1 and ask you to compute pressure at 2, right? So even if you don't remember this formula, you should be able to at least say that P2 has to be bigger than P1. So you have to add rho GH2, right? So just use intuition and common sense to kind of at least decide on the signs, right? The sign is one thing that students make a mistake on, right? So just be careful when it comes to the sign, if you're adding rho GH or subtracting it, right? Okay, so for me this intuition helps for consistency sake check to figure out the signs, right? Okay. Okay, so this last slide on this video is essentially a more common use of a manometer where you're measuring the difference in pressure across a duct where you have a fluid flowing, right? Or it can be a pipe where you have a liquid or flowing through it, right? So this difference in pressure can be measured using a manometer, and essentially it's an extension of of what we kind of learned in the previous slides, right? A combination of how a manometer barometer works and how you have, if you have different working fluids or different liquids, how you can find the pressure over stratified or layered liquids, right? Okay, so if we want to just go about, and this will be act as a good example, right? So essentially what we are trying to do is we are trying to find a relationship between pressure 1 and pressure 2 at these 2 points, right? That's all the goal is, right? So in this case, we start from point 1, and whenever it comes with different working fluids or different liquids, right, we try to find pressure at these intersection points of one end of the fluid to the other, right? Because when it comes to Pascal's law stated that it has to be the same fluid across which it can be applied, right? So you cannot apply, essentially say something about P1 directly with respect to this because it's two different liquids. That is, if you say point B and 1 directly, you cannot relate them because it's two different liquids there, right? So you have to, it's better to take it step by step, or that's what I would suggest, right? So let's go and kind of go through the steps, right? So if you want to find PA with respect to P1, right, what is the density here, right? It is rho 1, that is the density of this fluid. What is the net height, right? Net height is just h plus a between point 1 and a. So you have rho 1 g h plus a. Now the final question that I've said most students make mistake is in the sign here. Will it be plus or minus rho 1 g h plus a, right? So in this case, A is below 1, right? So pressure at A, you have a higher liquid column pushing down on A. So pressure at A will be higher. So P1, hence you will have to add P1 rho GH plus A to P1, right? Because that will ensure that PA is a bigger value than P1, right? So now that we know PA, right, can you find pressure at this edge here, let's say point C? So if you want to find point C with respect to PA, will C have a higher value of pressure than A, right? So the question is C at a higher location than A, let's say, right? Or we can rephrase it. Since C, it has a higher location, right, than A, your pressure at C will be smaller than A, right? So one way to kind of think about it is, even though you have a column of liquid through a pipe, and these are at two different points, let's say point A and C, this is literally equivalent to saying if you had a tank and you have it's filled with liquid and you have 2 points A and C, right? Since we talked about previously that there is no dependency or pressure horizontally, if you have different locations, it will always be the same pressure. The only dependency is on the height. So the pressure at A and C, the relationship between that is kind of same as saying as pressure at point A and C of a different tube. It's essentially equivalent, right? So if it's getting confusing in this tube shape, just think of it as a tank with a filled up liquid, right? Since it's a continuous fluid, you can say that, right? And that's the whole kind of principle behind Pascal's law as well. So when you're talking about pressure at C with relation to pressure at point A, right, since C is at a higher location, it should be smaller value than A, hence you'll subtract this weight of this liquid column, which is going to be rho 2, because this density is rho 2 for this orange liquid, and then G times the height, which is H, right? Finally, now you want to find pressure at 2 with respect to C, so P2 is equal to PC, and since P2 is at point 2 is at a higher location than C, you'll do the same thing, right? You'll subtract minus rho 1, now this is density of fluid is 1, times G times A. So if you substitute this PA, PC into this relationship, right? So if you put PA, you'll essentially get a relationship for P2, right? You can combine these three equations, right? And what you end up getting is, you have, if you put PA in here, you see essentially this first two terms, or these terms in the first relationship of PA becomes these first two terms here, right? P1 and then rho 1G A plus H. Now this next relationship or equation forms this third term here, right? You see minus rho 2 gh, and this last density or weight corresponding to the last column forms the last term here, and all of this is equal to P2, which is this, right? So you can combine these three equations to get this relationship, and now if you rewrite P1 and P2, you get a relationship or know the pressure difference between the 2 points 1 and 2 that we are concerned with. And you see that this A or height of A is not really important because it cancels off. You have rho 1 GA and you have rho 1 GA here, right? So the only thing that is important is the height of this working fluid that is there, and if you multiply that by gravity and the difference in pressure, you get the pressure difference in density, you get the difference in pressure between points 1 and 2. So this is how most of the times manometers are used, especially when it comes to measuring pressure difference in a moving fluid. And you'll see in the project we'll kind of be using a manometer in this sense to measure pressure difference about a model that we will put in a wind tunnel. Okay, and with that we will come to the end of this video. Again, like I always say, please, if some concepts are not clear, drop me an email and we can schedule office hours via Zoom to clarify some of these concepts. Thank you.